Computer. All right, there we go. Well, thank you for giving me an hour of your time, Dr. Szydagis. It has been fun interacting with you in the one group. How's your weekend been going?
Oh, extremely busy. I just had the prospective student open house for the university this morning.
Oh, how was that?
Oh, very busy. I brought a lot of cool demos to show off at the table, like a Newton's cradle, a plasma globe, all kinds of fun, toys for people who walk by to play with.
Okay. So, like I was saying in the email, this isn't really a UFO podcast. It's tangentially as UFO stuff on the side because it's more I don't know me documenting my misunderstanding in physics, inspired by a UFO experience I had 11 years ago. Um, that being said, my audience is rather small, but they like a lot of rigor and nuance, that and good communication. That being said, I want to spend a couple minutes just kind of building up like a baseline of general relativity, and you'll see where this is going. Just to make sure, like, so at like what level you can communicate with me with. So just like and this is stuff that you should like you probably already know. Like Einstein's equation, G mu nu is going to equal 8 pi G C to the fourth T mu nu, with that being your Einstein tensor and your stress energy tensor. So space-time curvature with a scalar coupling telling matter and energy how to flow. That's correct so far?
Yep.
Okay. So we don't really need to worry too much about T mu nu today. Just looking at G mu nu, really what this is, it's a way to compactify a 10 partial differential equations. So it's a tensor. So you have your matrix of your 0, 0, your 0, 1, 0, 2, 0, 3, 1, 0, 2, 0, 3, 0, 1, 1, 2, 2, 3, 3, with these being your clocks, rulers, and protractors.
Sorry, I have to stop you right there because I wasn't sure where we're going today. So I'm an experimental physicist, not a theoretical physicist. Those are very different things. So
Yep.
My knowledge of general relativity is very weak. The last time I had it was 2005 in a class, so 2004. So you're really talking to the wrong person. If you want to talk general relativity, you should talk to my colleague, for example, Professor Kevin Knuth, who knows more theoretical physics, because you're going to end up asking me questions very soon, rapidly, that are way beyond what I'm capable of answering, that are way over my head.
Oh, and it's I'm totally fine specking. This is more of a discussion. And I hope that's fine. And again, we're going to build a warp drive very very easily, and then from there it'll get into the paper on the UAP estimations of the really high G's. Just because I like visual analogies, right? So just kind of going off this, getting rid of the protractors, these combine your diagonal here. They combine basically into Pythagoras' theorem. So you have a ds squared equals dt squared minus dx minus dy minus dz squared. Sorry, it's super sloppy. This ends up being your line element for Minkowski or flat spacetime, which will relate to cosmology, and we'll get into that later. Really, so the Alcubierre metric is kind of a super simple expansion on this in many ways. So what is the Alcubierre metric? So let me just kind of get rid of this here, not worry about the other ones. Put a bracket here. Let's see.
But the Alcubierre metric is too simple. We know it doesn't work. That's why it was superseded by the work of Notario and Van de Broek.
Yes.
By Davis and Taylor and Lenz and many others. So it doesn't work because it's too simple. It assumes a zero-dimensional ship in a one-dimensional universe, and that doesn't work, and will require more negative energy than there exists as possible.
Yes. And so Alcubierre would totally be a toy model in this sense, exactly. like a toy semi-classical or pretty much classical approximation.
It's like a spherical cow.
Yes, yep. And that's what the shaping function describes. And actually, that's something that actually kind of bothers me. And like a lot of the literature is they'll show the Cuvier drive, and it'll be that, with the ship in the middle. But that's really the York time representation. Really, what the shaping function describes is actually the boost field, which looks more like that. And then you derive the shaping function out of that. But I digress here. The reason that not just Alcubierre, but I use Alcubierre as a model just to kind of build off, because that's what that's kind of what happens in the literature. But I'm bothered by the sense that when you look at a lot of the UFO or UAP people that are taking it seriously, you aside, because you obviously know this paper, but they don't. And I got a copy of it in here. They don't take into consideration the very high G accelerations. And often I see people trying to introduce new physics where they don't need to, and I'm not accusing you of this. When we kind of already have a whole class of mechanisms, warp drive, within existing physics, i.e. general relativity, where you could have something where you could get these really high apparent accelerations from an external, Eulerian observer, but from the inside of the ship, it's basically flat space-time.
Yes, that's right.
So, what I'm curious, so like the energy requirements for warp drives in most models, it's proportional, or it goes by the proportion by the velocity squared, right? And it's like, especially once you start getting above the speed of light, that's what really gets the energy requirements going super high. And what people like Borberg and Martire, for example, have pointed out is that when you're dealing with subluminal warp drives, not superluminal, so we have to walk before we could run, right? When you're dealing with subluminal warp drives, it really drives the energy demands way down. You don't have the horizon problem anymore. And
more important than that. No, it's much more significant than that. You no longer have a negative energy requirement.
Yes.
Yeah, that's crucial, because negative energy, I think, Martire is very, he really hates that. He calls it magical fairy dust, which really annoys Eric Davis, because we know negative energy exists. It's not magical fairy dust. However, the question is it ever going to be possible to harness it in large quantities? And that's an open question. But subliminal, I think, is much easier. You don't need any negative energy. You still need lots of energy, but none of it is negative, and that completely simplifies.
Yep. And like even the speed of light calculations, the lowest ones that I've seen were by Dr. Travis Taylor in his very recent paper that he did for radiance technology. I'm sure you've read it.
Yeah. He sent it to me before publishing it even, and I was like, Look, Travis, I'm not an expert on this. I'm honored that you sent this to me, but like, I'm really the wrong person, because I'm an experimental physicist. I build things. I don't use a chalkboard and write equations. It's not the type of physicist I am. I'm closer to an engineer than a mathematician, if that makes sense. Right? Yes. I'm an experimental physicist, so I use wrenches and screwdrivers as my primary.
So if I recall, he had the energy requirements for a warp drive, at least on paper. And again, there's always the difference between on paper and experiment, which you pointed out. I think he had all the way down to on the order of just a couple kilograms of mass energy for speed of light drive, which is, vast improvements over where the literature started 31 years ago. Kind of building into some of what Eric Davis has said and how you can kind of do this with still positive energies, but in some cases like negative pressures is some of the stuff that I've been reading. And Davis, I have his copies of Frontiers in Propulsion Science that I've been reading.
Well, I thought, so Eric Davis thinks you do always need some negative energy. I think maybe there's two Erics that you might be, it's potentially, I could be wrong, but I think you might be mixing up with Eric Lenz, who suggests that you only need positive energy. But Eric Davis is very insistent that negative energy is still required.
So Eric W. Davis?
Yes. Yeah, he's very insistent. I know him and I talk to him on a regular basis. He's quite insistent that negative energy is required. Maybe he has an older paper where he temporarily changed his mind, but he's pretty solid on that negative energy is required if you need to go FTL.
Yeah,
But yeah,
if you need to go
if you're
FTL.
talking about sublight, then yes, both Erics would agree that positive energy is all you.
Well, and this is something that's honestly it's kind of debated on even in kind of going on is because from the whole point of view of a warp drive is locally you're not actually breaking the speed of light at all, and
Yeah.
at this point this is
When I
starting
talk
to
about
get
FTL, I'm talking about FTL at a distance where it crosses the sky and it looks like it's FTL to you at a distance.
Yep. And honestly, this starts getting into energy conditions, which I wasn't expecting to get there quite yet. I mean, if you listen in the book, there's at least a half dozen situations in nature and in the laboratory where we can get violations of the null, weak, strong, and dominant energy condition, which were imposed on GR, back initially by Hermann Bode in the 50s when he was exploring the ideas of negative mass propulsion. But I'm digressing slightly. One of those being like negative pressure, and that's kind of what I was recently reading about there with Eric Davis. But in terms of the subluminal, and this kind of gets back onto the UAP flight estimations. If you can do this with positive mass and still have a very low g-force for the pilot, that's a way where you could have you wouldn't have to start getting into all these. I mean, you still have to get into exotic material science, but it's a different kind of material science versus something that would have to be able to withstand the brunt force of basically a 5,000 G impact.
Yeah, there's some serious problems. I've dug into Bob Reck and Mattew's work, and the issue is that you would need something like the mass of the Earth in the size of a refrigerator. That's some pretty hefty gravitational forces. So basically, what Bobrick and Mattew have done that's different, I wouldn't call it a warp drive per se. I mean, they would. But I think it's basically a way of weaponizing time dilation and making it even more effective. So that instead of just getting time dilation from going really fast, you get additional gravitational time dilation. So now a trip that, thanks to time dilation, was already reduced, like to Alpha Centauri, for example, from 4 years to a few months, maybe you can take those few months and reduce those down to hours now even. So I'm not downplaying what they've achieved at all. They just have created a different set of technical challenges.
Yeah, and they've put out a few different papers now at some point. They have the work factory, which I've been trying to play with. I'm trying to get that to work in GNU Octave because I don't have MATLAB. And that's been a whole other escapade. But
have you tried Octave? That's like the free.
Yeah, that's what I've been playing with. Their one paper they don't. All right, so they introduce a metric in their most recent one. But in their other one, titled "Introducing Physical Warp Drives," they go on how you're going to have 4 different classes of a warp drive, and then how some warp drives will have a warp bubble, and every warp bubble is a warp drive, but not necessarily vice versa. And many subluminal warp drives are more of a kind of a riding a warp field instead of being nested in a warp bubble. And in which case, you are going to have material science there, which can deal with the tidal forces. Actually, that's something that me and Dr. Glenn have been talking about. He got back to me because I guess the Navy cut his funding with the shutdown and stuff going off. So he started talking to me again. How I feel on that aside, have you read his paper on warp drives?
I read the one called "Introducing Physical Warp Drives," but
no, Dr. Chance Glenn, not Bobrick and Martyr.
Oh, Chance, no, I have not. No.
Okay.
I'm familiar with his name and work, but no, I have not. I remember that I said at the beginning of this call, you're asking about stuff I do not work on. Like you're talking to the wrong person today. I'm doing my best, but I think you might have picked the wrong person today because I'm literally like, I just can skim the surface non-mathematically and qualitatively for a lot of these things.
No, that's perfectly fine. Like this is it's a conversation as much as anything. In terms of like what he was doing, and then this might kind of get back into some applications and that you might have in terms of what you might want to look for in terms of tracking them. And actually, I think Taylor gets into that a little bit on his paper on the influence of the anisotropic matter in how it influenced the detection signatures that would come off of these things. But I'm taking a slight digression.
No one has fully solved the math. on, for example, how would any of these warp drives, I don't care if it's Bobrick or Lens or Alcubierre, nobody's actually done the math of what would that look like in an atmosphere. All the solutions are always in perfect vacuum because the math just gets way too hard. But this is where things like numerical relativity techniques and maybe, warp factory, right, created by Bobrick and Mattew at Applied Physics, and Martyr, I think he was how he prefers to pronounce his name. I think that there are better tools now to be able to do computational approximations and three-dimensional simulations of these situations.
Yeah, and so that's actually kind of what me and Dr. Glenham are working on. So his thing in very short 1 to 2 sentence elevator pitch is that when you're looking at the stress energy tensor, the team that I said we didn't really need to worry about too much today. So much for that. We won't get too deep. If you have an anisotropic medium has a complex permeativity with an imaginary part greater than a real part, when you plug that back into Einstein's equation, it kicks the energy density out as a positive instead of a negative, which is good for a few reasons. Where we've kind of been expanding on that is how atmospheric plasmas are already such a medium that have exactly those types of characteristics. So they wouldn't be producing a warp field yet, but it seems, at least preliminarily speaking, that they could be manipulated to produce a slight tidal effect to kind of tug on the craft, and that's kind of why we're dubbing it warp-assisted hypersonics. But it's a work in progress.
Okay. Cool.
The thing with warp drive, though, is if you start taking it seriously superluminally, and this gets back into whether or not the energy conditions that we use in general relativity are valid. And let's be honest, they're assumptions. They're not.
They're not valid, and this is one of Eric Davis's points. And there's even a paper you probably read already called Twilight of the Energy Conditions. They're all broken. They're broken by quantum mechanics. They're broken when you look at relativistic, when you look at quantum field theory, right? So the problem is with general relativity is that it's a classical theory. It doesn't obey quantum rules. And so basically you've got things like the time energy, Heisenberg uncertainty relation. You can break any of the energy conditions you want. You just can't do it for too long. But you can still break them, which is quite remarkable.
Yep. Or on cosmological scales, which is another area of research too.
On cosmological scales can be violated as well. On microscopic scales, they're really only valid on sort of like the human daily life scale, right? It's not easy to violate the energy conditions. It's sort of like the human life on a planet mesoscopic scale, but at subatomic levels as well as cosmological levels, there are exceptions, known exceptions, up the wazoo. I mean, the discovery of dark energy already that's a violation of one of the original energy conditions. Yep. It's a weird thing. And now we think the latest data shows that it's phantom dark energy. Wow, even worse. So then the density goes up with time. So it's a gross violation of our common sense notions of conservation.
The density, it actually goes down on type of scales like negative A squares with the data fitting on density. I do have papers on that. 2 binders.
Some theorists have interpreted some of the latest data as suggesting actually a phantom dark energy where W is more negative than -1, which would mean that actually density is growing with time. And clearly we don't know what's going on because some papers are claiming growing, some people decreasing, some people are doubling down that's constant. I think we don't know until we get more data and better data.
Yeah, so right now, so it's not at 5 sigma either way yet. The highest that I've seen, and again, I can cite the paper for this, is 4.2 sigma in favor of a very small but positive cosmological constant that actually decays.
Well, that makes more physical sense. Yeah, decay makes more sense. Increasing with time is really a gross violation of our common sense energy conditions.
100%. And the whole and we'll probably circle back around to this, depending on how we do for time. There's a lot for us to brush over. The whole reason the energy conditions were proposed in the first place was out of pretty much the Chapel Hill Conference of 1957, when you had Wheeler and Bondy were considering things like he had the paper on negative mass propulsion, which is basically like a 50s precursor to the warp drive, but in a more classical sense, where if you have a positive mass and a negative mass, they'll chase each other off to unbounded accelerations.
Yeah, I covered this in my recent exotic propulsion class. It's really a shame you didn't take that class, or did you? No, you didn't take my class.
No, I didn't.
Okay, that was the last time I was teaching it. I'm not going to have time again, so that's too bad. I covered that as one of my examples.
Yeah, and so the other one from Bondy was back then it was called Einstein-Rosen bridge, because I don't think Wheeler had came up with the term wormhole yet. But ultimately the reason was they wanted to limit systems within general relativity that would force them to really start to question the nature of causality, because that's kind of where this math starts to lead. When you really start taking FTL systems, seriously, you can start getting into like virtual causal signaling, or using them as time machines in certain scenarios, and that's there are certain implications that have to come with that. There's paradox and all this other stuff. I believe you gave a TED talk on this.
I did. I gave a 17-minute TED talk on time travel. That's right. It was supposed to be a 5-minute talk, but with a topic like time travel, you can't do it justice in such a small amount of time. The real version of my talk is like 2-3 hours. I did that in person locally a couple of times. In one case, there was in a room that's supposed to house only 20 people. I had 100 people come because it's a very popular topic. But I'm not the expert on that. I talked about it for fun. The real expert on that is Professor Ron Mallett at University of Connecticut Storrs.
Honestly, I'd say today the expert would actually probably be Dr. Barak Shoshani out of Brock University. He's been doing some really good work on that. He's put out a series of papers starting in 2019, kind of building on Mallett and also David Deutsch's work, and also Novikov, and he has basically a whole lecture series, and then papers going along with it.
Well, I'm biased because I know Ron. I'm friends with. I've met Ron Mallett. So
I'm not trying to detract from Ron.
Yeah.
I'm not trying to detract from him. I was just say probably before 2019, I'd say Ron was probably the expert on it.
No, but I read Deutsch's work and Seth Lloyd's, and obviously Novikov is famous for his self-consistency principle.
Yeah. So what Shoshani kind of he goes and does, he builds off Deutsch, and he kind of goes through and he starts to really take the mathematics side, and he's very thorough in his derivations and on the appendices, and he provides all the math with it. That once you start taking into consideration all the paradoxes that you can invoke, that you can get to arise out of these various FTL scenarios, and the time travel implications that come with it, it's all right. Throwing Hawking's conjecture out the window, because that's boring for the sake of this conversation. Novikov is perfectly sufficient to solve some paradoxes that can arise in situations that you can set up, but not all of them. It turns out that you need some type of multiple branching timeline scenario in order to account for all these paradoxes, and so you can have everything so it's paradox free. Thankfully, again, building off Deutsch, the framework that we have for that is going to be that proposed initially by Hugh Everett in the 1950s. And so he goes and he shows a couple of papers that you can use wormholes, and his most recent one was on warp drives, is that you can use warp drives to make CTCs and an Everettian like multiverse. This actually was very fascinating series of papers to read. Excuse me.
Yeah, I wish I had time. I look at there's so much incredible more stuff that's been written,
and it's hard to keep up with all the literature too. Going with like the whole Everett thing, and again, I know you're not really a theorist, but there are certain experimental models that kind of seem to favor a worldview in which the wave function is a real, physical object somehow, and is not merely just like an epistemological tool keeping or bookkeeping tool that you can use to shut up and calculate. Again, Everett and Deutsch kind of go very deep into this. Is that something you've ever kind of looked into, at least? Just,
only a little bit when I was preparing for my talk those many years ago, my TEDx talk.
Okay. Do you have any intuitions?
I don't, unfortunately. This is it's not really my field anymore. I don't really spend a lot of time on it.
So, one of the unfortunate things that happened with Everett, so his original, it's called the long thesis because it was like 137 pages was his long thesis, and it was very.
Did you say 137 pages?
It was 127 or 100. It was over 100 pages. His long thesis.
Because it was 137. That's 1 over the fine structure constant. So that would be remarkable.
That'd be funny. I wonder if that. I'll have to check. I'll have to check that now. I have a copy of it right over there. But I can check after. Anyways, he ended up having to strip a lot of the sections out and a lot of the compelling arguments out to have his actual published thesis, now called the short thesis, which was titled the relative state formulation of quantum mechanics. It was published alongside the proceedings of the Chapel Hill Conference, not with it, alongside it. Anyways, I digress there. Part of the reason that he cut it down, at least historically speaking, I'm a big history nut here too. Sorry for the slight digression here, but is that because his thesis advisor, John Wheeler, was a very loyal student of Niels Bohr, and Niels Bohr was a fierce defender of the Heisenberg interpretation of quantum mechanics. And so he had Everett cut probably 2/3 of the paper in order to better appeal to Niels Bohr, which is a shame because how the field of that version of quantum mechanics, the many worlds interpretation, it progressed in a way where Everett didn't fully intend it to. What do I mean by this? It was used entirely with the time-dependent, non-relativistic version of the Schrodinger equation, which is fine at most laboratory scales, and in which case you're going to get the predictions that version of quantum mechanics makes is going to be indistinguishable, no difference from Heisenberg quantum mechanics, where you have the wave function collapse, which is an extra axiom that was put on because we didn't want to have to deal with the wave function saying it spread out into these multiple universes that we didn't see. One of the aspects that he cut out about it, and this ended up being the inspiration for the Wheeler-DeWitt equation, HSI = 0, that's used often in quantum cosmology, is that, how do I want to word this? He has a whole information theoretic approach where he talks about the system as a pure state, and then local subsections of it that are non-relativistic and deal with the time-dependent Schrodinger equation. But the whole system globally was actually a pure state of zero entropy, and that's something that kind of got shuffled aside and kind of got thrown only in quantum cosmology because it doesn't derive enough at all laboratory scales for it to be useful or to be of any difference there, which is part of the reason that there's been quite a few misconceptions in the field of Everettian quantum mechanics. But where it does start to derive is in these cosmological scale predictions, in which case we start seeing a difference in the predictions that this pure Everettian quantum mechanics is going to make, again at the cosmological scale versus the LCDM, the lambda cold dark matter cosmology that's based on the standard model. What's interesting about that is, and people have started to explore this, like Maya Bonowitz. She's working with Dr. Nyasha Forty out of Perimeter Institute. They're working on a series of papers around explicitly this. which is actually really, really fat. And again, I can provide you copies of all these papers. I have binders full right here, so I can send it to you.
I won't have time to read that.
That's fair enough.
Yeah, I mean, I'm so busy between my dark matter work and my nuclear energy work and UFOs and UAP. Right, I work 400% time. Like I don't get free time.
Well, and this is why I really appreciate this hour.
Yeah.
And so what kind of happened? So, all right. So what are some of the differences with at the cosmological scale? And this will get into dark matter here in a second. So there is a method that my Matt is here. All right. So why does LCDM have the state that the state of the universe that it has? We want the cosmological constant to be a constant, i.e., why it's the lambda part of it, and then the CDM, the cold dark matter, which a lot of people think are WIMPs, weakly interacting massive particles, is one theory. There's other people who say we don't understand gravity. I think that's a cop out. I don't like people who say that.
People get angry when I say this, but that ship has sailed. I mean, we've disproven Mond and many of its cousins so many times over and over and over again that it's just like, I just laugh now. I mean, we've tried that idea. I mean, it wasn't a bad idea in the 70s, 80s. It was a very good idea to try to say there's no dark matter. We don't understand gravity. Excellent idea. We tried it. It didn't work. Time to move on. I mean, it's as simple as that. And people get angry with me, and I'm like, look, maybe I'm wrong. And maybe there's no dark matter. That's cool. I'm fine with that. I'm not some dogmatic, like in your face, oh, there's dark matter just because I look for it. I'd be perfectly content if it didn't exist. However, it just frustrates me. There's like 8 pieces of evidence, and people with modified gravity ideas usually can get to 1, 2. The maximum I've seen is maybe 3. I've never seen a modified gravity theory that addresses all 7 or 8 independent piece of evidence of dark matter. So yeah, I'm not going to expend a bunch of my intellectual energy on it anymore.
So one of the all right. So like on the how do I want to? There's a couple different ways I could take this. All right. So like with the cosmological constant being a constant, there's a certain the universe kind of expands exponentially, eventually out of the heat death. That's why, some of these stuff with the cosmological constant tensions, like in the Hubble tension, are kind of an issue. They call it one of the crises in cosmology. But in Everettian quantum mechanics, and there's people that have found this, you don't need to quantize or unify gravity anymore. Because it's actually emergent via entropy. Yes, and that's why, again, it's so important that you talk to my colleague, Professor Kevin Knuth. That's exactly one of his favorite ideas, and he's writing papers in that direction now. So, but anyway, sorry, I interrupted you. Please continue. That's a very valid hypothesis. It's a good idea. And so what? All right. So what's one reason that you might want to have the cosmological constant be a constant, at least building up from the standard model quantum?
I'll tell you, because for simplicity, it's the simplest approach for several reasons. First,
unitarity.
Mathematically speaking, you don't have any free parameters then, right? It's always nice to have one number versus 2. That's the mathematical reason, which is kind of a silly reason. Then there's the actual physics motivated. The physics motivated reason is that if it's a cosmological constant, then it's exactly the same thing as the quantum mechanical 0-point energy, probably the same thing. And that means that it's just virtual particle-antiparticle pairs popping in and out of existence. And then there would be a cosmological constant. But if it's not a constant, then you can no longer make the claim that it might be synonymous with the 0-point. That's why.
And this is going to tie in perfectly as to why this more extended pure Everettian version of quantum mechanics kind of solves one of some of these cosmological discrepancies. Mm-hmm. And you just hit on one of them, is the vacuum expectation value. According to quantum mechanics, as we teach it textbookly, in order to preserve unitarity, as we run the equations, we would expect the vacuum expectation value to be, roughly 120 orders of magnitude higher than what it actually is.
Yeah, it's a serious problem. It's one of the greatest discrepancies in all science. And that would tend to suggest that the dark energy is not the same as the 0 point energy because of that massive discrepancy. That would seem to disprove that simple hypothesis.
But one of the reasons that motivates that is the idea of unitarity, right? Mm-hmm. In some papers, so the idea that as you evolve the quantum system in time, in order to preserve unitarity, all the probabilities have to add up to 1, right? That's the whole concept of unitarity.
Yep.
All right. So as space time evolves out, you have your starting eigenstate at t equals 0, and then you go t equals 1. You'll have you're spread out, and then it'll spread out again. As you do your dice flip and you turn these to probabilities and you observe a state, at least in classical quantum mechanics, all of the energy in one of these, all of these go away, and the energy kind of goes into this, and now this is now your new starting eigenstate. In order so the probability still adds up to 1. That's the process, the collapse of the wave function. There's a whole bunch of debating people about what exactly goes on in that process. That's not exactly what I'm here to talk about today. The thing is if you just let the system spread out into the different eigenstates, it turns out that your vacuum expectation value in that particular branch of the wave function comes out to be a very small but positive cosmological constant that would decay with time as the wave function spreads out. Where are the other 120 orders of magnitude of energy? They're spread out in the wave function.
Wait, did you come up with this on your own? Is this an existing paper? That's an incredibly good idea. I like it.
I mean, it's an idea I've been playing with for a while, but I'm not the first one to think about it. I can point you to a whole bunch of papers that kind of lead in this direction.
I've never heard this before, because remember, I'm not a theorist, so I don't read all the theoretical papers. I'm more concerned about what I can measure, now, today in the lab. But I can still appreciate the mathematical beauty of the concept you just.
Now, this is where it starts to get cool. You start to get this.
Oh no, it's already cool. No, it's already cool.
It's cool.
Keep going, yeah.
So you start to get this interaction. So one of the things that I said there starts to be a couple differences in the predictions. That's kind of one of them, and it kind of solves that thing. One of the other things that it starts to predict, or like I said, was how the vacuum in each particular eigenstate is going to decay by the cosmological factor, so by a to the negative squared. So it decays with time, so that's natural there. Black holes, interestingly, become cosmologically coupled objects to the cosmic event horizon, and they grow because you have the discrepancy between the volume, between surface area and volume. They grow as a to the third. Interestingly enough, not just supermassive black holes, but all black holes. Now, there's a very small energy scale region where actually Hawking radiation will still take over and cause a super small black hole to decay, but it lowers that threshold a little bit, and there becomes a point where the cosmological coupling starts to take over, and you would end up at early universe and then persistent throughout the universe. Black holes are going to have a higher mass than what LCDM predicts. Now,
wait. So instead of lower mass, like you get with Hawking radiation, they'd actually get bigger with time?
Yeah, they grow bigger with time because they're cosmologically coupled to the cosmic event horizon, which is shrinking, and so and the smaller ones inside actually get bigger. The connection there.
Some sort of new conservation law going on there then?
Globally,
okay.
Because remember, you're dealing with every across every universe, and how there's
gotcha.
Energy dynamics end up becoming a bulk phenomenon, dual to a timeless boundary theory. So it's holography, but it's not ADS. It's not anti-de Sitter space holography. It's actually de Sitter space holography. So it's a similar but related thing that's less explored, but in my opinion, more valid.
Okay.
Now, let's think about this for a minute. If functionally every black hole is going to have more mass in it than what our existing theories of gravity in it, there's going to be extra mass there that, we're not accounting for, but we would still observe.
So dark matter, in other words.
Yes, so dark energy condensates into dark matter in the form of cosmologically coupled black holes.
Ah, okay. This sounds similar to the work of, are you familiar with papers by Harry Ringermacher?
Ringer sounds familiar.
You need to, I put the name in the chat because it's a little weird to
Ringermacher. Okay,
I'll
look that up.
Harry Ringermacher. His co-author is Larry Mead, MEAD. They have at least one paper on this idea, or a similar one. Not identical to what you just said, but very similar.
Yep.
And it's from a few years ago, 5-10 years ago, maybe, that show that they talk about dark energy condensing into dark matter. So definitely check that out.
And I don't know if you can see here, but we actually have the equation that kind of shows the dual.
No, unfortunately, it's out of focus.
Oh, okay.
When you write on the board behind you, I can see it.
Okay.
To my right, to your left, is unfortunately out of focus.
And I can send you papers on this. But so what happens is what seems like energy dynamics in the 3+1 bulk where we are is actually a phase rotation on the global boundary, and phase rotations famously leave a system unchanged, i.e., no global energy change. Even though it seems like dynamically, there ends up being like there's a coupling, there's a wormhole coupling between a white hole and a black hole. The difference between regular black hole cosmology is that the inside of black holes is not a new universe. It's that it's connected via like a wormhole manifold, so to speak. I think technically the terminology is used as an orbifold. I'll have to double check that. Where the Big Bang at the beginning of time is the white hole emitter, and every black hole in the multiverse is the sink. And so that's where you have like a seeming energy flow from. But globally, it's really just a phase rotation on this boundary. It's super interesting to think about. One of the things that comes with it is it's a way that you can reverse predict, because the rate of rotation of this global boundary is you get out light cones, which you end up getting your null GeoD6, and you have your space-like and light cones. And it turns out if you can figure out a way to warp space-time locally, which will actually look like a larger rotation on the boundary, you can get your light cone to overlap with a past adjacent light cone in the multiverse. So if you have a way of warping space-time around like a craft, for example, and you can go FTL relative to one eigenstate, you can use a warp drive, at least in principle, according to this theory, to travel. It's like a form of time travel in the multiverse.
I think I've seen probably Hollywood movies that have a similar concept, but yeah, it'd be hard to see how one could turn that into a practical reality in the real world.
There are, some Hollywood movies about it, and I kind of rub them the wrong way because I feel like it puts a bad stigma of some of the serious research that's going into this. Like, oh, you've been watching too many movies.
Yeah.
Like, there's a lot of serious research that's actually going into this.
There is.
Yeah, exactly,
it's like UFOs. Yeah, people laugh at that, but there's serious research going on also by serious people.
So kind of how this ties back to warp drive is that when you're massaging with these equations, the mechanism that you would want to traverse the Everettian multiverse, and again in this worldview that solves many of the cosmological issues, or solves many of the issues we have in physics simply by removing the axiom of the collapse of the wave function, you can use a warp drive to hop around the multiverse in this weird way. Now, that starts to tie back into some of the UAP stuff. We were talking last time on the group chat about how some of us are starting to think about how maybe there's some kind of weird CTC thing going on here.
Oh yeah, I mean, you must be familiar with the work of Mike Masters. He thinks that all flying saucers are time machines. You read it? You read his work?
Yep.
Yeah.
And I don't. I agree and disagree with Mike on a lot of things. I agree with him that a lot of these are time machines, though I think he needs to explore the Everett version of this because he's too caught up in paradoxes. But also, his idea that an alien on another planet wouldn't evolve into a hominid, I find is flawed because the idea of convergent evolution is still a thing.
Yep. Yep. I agree with you. I think I also think we're oversimplifying things, and it's an all of the above approach. Why
Yes.
can't some things be from other universes? The IDH. Why can't some be aliens, and why can't some be time travelers? Why isn't it all of the above? Right? It could be that we are trying to oversimplify a very very complex phenomenon.
So I think I know we're starting to get short on time here, but
But same thing with dark matter is I'm actually briefly going back to something we said earlier. I'm not convinced that it's either or dark matter or modified gravity. What if we need to modify gravity a little bit and we need dark matter? I think, again, we are grossly oversimplifying our complicated world.
oh, for sure. Yeah, and there's and the whole thing with like the Everettian thing, and how when you maximally extend that, it's not that it gets rid of the need for dark matter entirely, but it seems to be a better fit for the data that we're getting with less starting axioms, and it would put tighter constraints on what you'd be looking for in terms of dark matter. Does that make sense?
It does, yes. Yes, it does.
Now, kind of to tie some of this back into the UAP stuff, I think a powerful analogy. Are you familiar with North Sentinel Island?
With what? I'm sorry?
North Sentinel Island.
No, I'm not, unfortunately.
Oh, this is fascinating. So this is like a real world case of the zoo hypothesis. You have this largely uncontacted tribe. I said largely, not entirely. In the Andaman Islands, in the Indian Ocean.
Oh, okay. This sounds familiar. This is one of those uncontacted tribe stories where they're like Stone Age in the 20th century.
Yep.
Okay, I just forgot the name of the island, but I think I know the story. But please continue.
And they're protected by the Indian government, by the Indian Navy. So you're not supposed to intrude on their water space or go on their island. And they've had some past bad experiences with some islanders or people trying to go on the island with like forced conversions and stuff like that. And it's kind of the point where anybody who does set foot on the island ends up getting arrowed to death. But a couple things have happened. Ships have crashed there, like larger cargo ships, and we haven't been able to go get them. So they have access to modern materials. They just don't know what they're used for, which is already a fascinating case study on its own. But the very few positive interactions that have happened with the population of this island have been when they're on their fishing canoes, out fishing in the water, and they see another fisherman, and they might exchange fish, and there's a friendly interaction. Now, what's the difference here? If you go onto their island, you're dead. But if you talk to them out in the water, there's a chance for some more mutual recognition and positive interaction. If we're using this as a real-world scenario of the zoo hypothesis, perhaps it might be worth some of science's time to try to reproduce the next prediction of general relativity, i.e. a warp drive, in order so we can have our canoe to go and pull up aside these UAPs, and instead of trying to, and again, I still think that we should be studying telemetry and all this other stuff, that we should be keeping track of our skies for, whole other reasons aside, but...
No, but this sounds exactly like, if you're a fan of Star Trek, then you know about the Prime Directive. You're not allowed to talk to alien species until they've built their warp canoes, right? That's the whole thing. The whole thing of the Prime Directive is General Starfleet, General Order Number 1, is pre-warp civilizations you're not permitted to speak with them. It's like they're in the zoo, right? But if they leave the zoo, then you can now welcome into the Galactic Federation, right?
I don't think that's a bad analogy for what might be happening.
Yeah, it's fiction, but sometimes good fiction, good science fiction does mirror reality.
Mm-hmm. I mean, yeah. No, that's actually a really good way of looking at it.
I mean, Jules Verne predicted the internet in the mid-19th century. I mean, sometimes a lot of writers of fiction are very prescient, very prophetic, even when they don't intend to be, even when they're just having fun.
Mm-hmm. Oh, for sure, for sure. And so again, I think that's a way that I think that more UFO and probably some university research should be going towards is a signatures of warp drives, because that seems to be the prime candidate of what the mechanism at play here is, at least without trying to introduce new physics. Let's try to expend existing physics answers that we have.
I gave a talk suggesting just that at a SETI workshop at Ohio State University last summer. You should have seen the temperature drop in the room and the hate that I got. Well, part of it's because then I started talking about UFOs. If I had just stopped and not kept going, it would have been fine. But I suggested using LIGO, using existing gravitational wave observatories.
Well, LIGO, you couldn't use LIGO. So there's been papers on that.
Yeah, but Travis Taylor was furious. He came up with the idea first. He suggested to LIGO. They laughed at him, and then they turned around, stole the idea, and published on it. So yeah, I know that's life, right? That's life. Yeah.
Yeah. But and again, like, general relativity is already a very successive. It's our most successful theory other than quantum mechanics, and it seems like, again, we can get general relativity as an emergent property of a more pure version of quantum mechanics. And pretty much everything that GR has predicted so far has been confirmed one way or another. So, I mean, we're starting to tick down on the list here of things that have been confirmed versus things that, we're past gravitational waves. We've passed the, merging of black holes. We've passed there's a lot of things. We should start taking warp drive more seriously.
I agree, especially so a subliminal one doesn't require to do any sort of mind bending whatsoever. And in fact, in the book The Physics of Star Trek, there's a statement made that, look, and I've said this myself in many, many talks, maybe you've heard me on YouTube podcasts saying this, is that if you had a warp drive, you would be an idiot not to use it to go any speed, even 30 miles an hour. Like, it's such a great idea. Warping space-time is such a good idea, even though it's so advanced and speculative, that you would use it for any speed.
Like the holy grail of physics engineering, in some sense.
Yeah, because why would you ever use anything else? So this is a mistake that Star Trek makes, actually, is there's warp drive and impulse engines. Why wouldn't you always use the warp drive at any speed? It's just a vastly superior technology because it doesn't require any propellant. You don't need to eject something behind yourself like a rocket.
And even as far as warp drives go, like I was saying, we have to walk before we can run too. I mean, the idea is that, we can still use a warp drive to assist existing propulsion platforms until we make them good enough to use on their own. So, like, there is a progression that can be made. I mean, I think a lot of the research being done into the FTL, while it's great and I really like it because I'm very much into the time travel aspect of it, and I think that should still be researched, is that we need to look at the subliminal side a lot more seriously.
I totally agree with you. Absolutely. And this is where Martyr, Bobrick, they're really pioneers on this, although they do disagree with Eric Davis, who thinks, no, we need negative energy and faster than light. And I like Eric. I'm friends with Eric W. Davis, but I think that it's important to have opposing perspectives and respectful disagreements, something we have forgotten how to do in this country, especially because in order to find the truth, that's how we find truth. Science should be a debate and a dialectical process by which the truth is sifted out.
Well, and I think a really easy paper for, not that I'm telling you guys how to do your jobs, but for people like you and Dr. Knuth and Dr. Davis to put out would be maybe a follow-up to the flight characteristics, estimation of the flight characteristics of UAP. But instead, because all the estimates in there are for like a relativistic rocket and the energy requirements that you would have to have for that, which is great. That's good baseline control math to have. But if we're going to take the warp drive hypothesis seriously, we should redo the calculations, but for various warp metrics, from Alcubierre and Ontario to Vandenbroek, of them doing similar maneuvers that we've tracked UAPs doing. So instead of doing, 10 times the speed of light for our velocity parameter, because again, the energy goes by the velocity squared, we do, 10 times the speed of sound, or, accelerating to whatever data, you guys have to put into that.
Yeah. Yep. I think Kevin had this idea. He wants to try to recruit Eric to work on this. Is Kevin just a couple weeks ago? So it's an interesting synchronicity. He was pointing out to me he would love to do calculations for like what does a warp drive look like in atmosphere, and he's the one. He's one of the 3 authors of the entropy paper about the calculating using the standard relativistic speeds and the energy requirements there. So, but I think if I'm not mistaken, the energy requirements will be much worse. It'll be insane. Energy requirements are already bad, but now if we're going to warp space-time, they might be much worse. The benefit of warping space-time is not necessarily the energy requirements are lower, but rather that you don't need any kind of propellant, and so it kind of changes the equation in terms of fuel and propellant, things like that. However, it still might require an astronomical amount of energy.
And that's why I was saying that it would probably be worth it to do a sampling of, start with Alcubierre because that's the baseline of the field, and then go into Notario and Van den Broek and Lentz, and then eventually to Travis Taylor, where I think, where his is the lowest that I've seen so far. And again, he was doing speed of light calculations still. Take his baseline of, I think it was 100,000 layers at like 10 microns or something like that. I'd have to
so there's layers, like Travis Taylor talks about this as well. Pulsation, there's all kinds of tricks you could use to maybe get the energy requirements down. And maybe warping space-time would actually end up being less energy than like actually zooming near the speed of light with traditional propulsion. You're right, that it may turn out to be more energy effective than
I think it'd be worth at least modeling and looking at and seeing what are the warp requirements, and B, how low can we massage them just based on existing literature?
Yeah, I wish I could clone myself. And I would make the clone teach my classes, so then I could go work on things like this. But yeah, my time is so limited. But I'm going to talk to Kevin, and I'm going to talk to Eric about some of the things you shared with me today, because I want to see if I can get them interested.
Okay, and if they have any questions too, like feel free to give them my contact information, because I'd be happy to answer any questions.
Yeah.
We are about at an hour here, and I know that's all you said you had today. So
yeah, I gotta. Unfortunately, speaking of classes, I do need to get to work on preparing my lectures for the week. So most normal people, the weekend is a break. But for me, it's time to catch up on like, okay, prep my lecture slide for the week for class. So yeah, Saturdays are not days off for me, unfortunately.
Well, again, thank you so much for your time.
Oh, you're welcome.
It was very good to have a one-on-one with you finally.
Yeah, it was fun. So, you're gonna post this to your YouTube channel?
If that's fine, is there anything you want me to take out?
No, okay. Certainly not. Yeah. No, everything is fine. I didn't spill any secrets. I don't know any secrets. I wish I did, right? I wish the government hired me to like work on UFOs. So I don't know any secrets worth telling.
All right. Well, I'll let you get to your classwork. Hopefully we can do this again sometime.
All right. You take care.
All right. Thank you so much. Have a good day.
All right. Bye.